Today we are going to learn a very interesting topics that is wave propagation. So it's basically if you are a mechanical engineering student, you know that aircraft wing are run very high speed, and that's the Mach number is very higher. That's it's greater than one. And let's us talk about some basics that help your thoughts and simulation. So here we see the slide that is normally a aircraft wing is run very high speed, and Mach, we know that Mach number is the velocity of fluid divided by velocity of sound velocity. So there's the ratio is Mach number, and normally aircraft wing Mach number is zero. Normally three is higher than one, so supersonic velocity, and we know that. Okay. Case 3, here we see the case 3 wave propagation when the Mach number is higher than 1, then the is Mach cone is this type of shape, that means cone shape are formed. So we are simulate this formation and investigate that our simulation result and this theoretical result are almost same here. So we know that there are two types of flow in a fluid. One is compressible flow and another one is incompressible flow. So compressible flow is basically when the fluid flow is uh, insignificant variation, density variation due to change in pressure and temperature. So when the pressure and temperature are insignificant for the varying density, that is called compressible flow. And we know that aircraft wing are so much higher speed, and there the pressure and temperature are significant to contribute the variation of density. That's why in our case we are consider here the flow is compressible flow. Also we discuss later for the simulation. Also here we consider the flow is inviscid because the Reynolds number is so much higher for a aircraft wing velocity, because the viscous effect are very negligible here. That's why we consider the inviscid flow model. So our problem is our main determination is to simulate the aircraft wing velocity for a creating a shape Mach cone, by creating a Mach cone for Mach number 3. So that is supersonic velocity. So let's go into our workbench. So here I already open our workbench file. Okay, this is our workbench display here. So we are simulate our model in ANSYS fluid flow fluent. So first we create our geometry here. So we open the ANSYS design modular to draw our geometry. Okay, first of all in XY plane. Okay, first of all we draw a rectangle here. So here we draw a random rectangle. Okay, so then the constraint is our symmetry. So we first cursor in our axis, then this vertical line, that is symmetric here, and we put down our dimension also. So our dimension in x direction, the horizontal length is almost 2 meter, and the vertical width is here 0.3. You can choose your random dimension, so I choose here. And then we draw our wing. So uh, let's zoom again. Okay, okay, that's inside intersect here, then intersect here, then intersect here, and then here. Okay, so let's constrain the point, so midpoint. Okay, and this line and this line are meet, and this line and this line also meet, this line and this point also midpoint, and Similarly, this point and that point are midpoint. Okay, so we almost finish our dimension. So let's modify something. So we don't need the rectangle here, so we just trim it. Okay, okay, let's okay, and we here we delete also. So cut this point. Okay, and press the delete button. So delete. Okay, that is our main wing geometry. Also, we draw our pressure line. So also in draw, then rectangle, and draw a pressure line. So that is our pressure line, and same as constrained by symmetry. So this line, that line, and that line is symmetric. Okay, and put down the dimension here. So let's talk about dimension. So our width is 30. Sorry, width is our 50. So width or 50 here, and the height is 30 30 here. And also this center length and this length is also 10 meters. So we choose this point and this point. Sorry, Control Z. So delete here. So general, this point, something missing here. So A6 delete. So this line and this line, something wrong here. So let's again uh, this point and this point, general dimension. Okay, so we put down the dimension here. So this dimension is 10 meter. So this is 10 meters. So, and this dimension is 10 meters. So okay, that is 10 meters. So this is our geometry here, and we need to sketches. So surface from sketches, and we select the sketch 1, add material, and operation is our material is frozen, so we need to frozen here and then generate it. Okay, that is our main geometry. And okay, let's talk about meshing. So we go to the mesh. Meshing is too important for accurating the predict the result. So you need to learn about meshing, and perfect meshing gives your perfect result. So okay, this is our geometry here. So okay, z axis. Okay, then meshing. So we need to mesh our fine mesh. So insert sizing. So we need to proper mesh in our wing side. So that is our wing, and we need to perfect mesh for this. So control, we are selecting 4 points, 4 edges. Okay, then surface mesh. Then we need to element size is almost 10 millimeter. Also we need to face meshing, sizing, then this domain. So that is this edge, this pressure edge. So pressure edge also, element size is almost 50. 50 is too small, so 100. Okay, then generate mesh. Normally meshing takes 2 times here, because we used here in fine mesh, that's why it's take 2 time. Let's wait something. Fast, 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 man. Okay, my meshing is almost complete. So one task is remaining here. So we should name the edges. So this edge and this edge, this 4 edge is we named the aircraft wing. Okay, and the outer edges, this edge, control this edge, this and this 4 edge we named the pressure wall edge. Okay. Okay, you can see our aircraft wing location and the pressure wall edge location. So our meshing is almost done here. So update the mesh. So let's go into the setup section. So we use here double precision, that gives fine accuracy of result. Okay, you can see our geometry is here. Okay, let's set up our model and boundary conditions. So in general section, I already told you that our flow is compressible flow, where the density is so much variant due to pressure and temperature. So you use here in density based solver type, and okay, then go to the model, and we use energy equation because temperature is fluctuating here in our problem, so we use energy equation. And in viscous model we use inviscid model, because here the Reynolds number is so much higher, that's why the viscous effect is negligible, so we use here inviscid flow. Okay, let's talk about material. We use air, so we use air material here. and the density is for ideal gas density, and change and close. Okay, in cell zone condition we use surface body here, fluid, and in edit section let's check air. Okay, it's air. Okay, let's done about it. Let's go into the boundary condition. So in pressure voltage, so we use pressure voltage and pressure far field. So we use Gauss pressure is 1 atmosphere, that is 101,325 Pascal, 325 Pascal, and we use Mach number is 3 because our flow is compressible flow. So Mach number is 3, that is okay. Then in thermal temperature is 27 degrees Celsius, that means 300 Kelvin. Okay, that's done. So operating condition we used 0 Pascal. Okay, our boundary condition is almost done. In reference value, okay, let's go to the reference value. Reference value gives here the 0 Pascal. So we compute from the pressure wall H that show the pressure is 0.101325 Pascal. Okay, it's done here. And then methods, go to the method. We use implicit method and also use green Gauss cell based theory. Okay, then control. Okay, here not monitors. We go the monitors and residual, and we set a criteria for our continuity equation. We gives it gives your result so much accurate. So we use the criteria is 1 into 10 inverse 10. So that gives us so precise result. Okay. So our almost done here. Initialization. We use standard initialization, and pressure wall zone. Here see the velocity and Gauss pressure, and initialize our problem. Okay, initialization is done. So then run the calculation. Number of iteration we choose 300. So one thing remember that we are main our main task is to determine the Mach cone here, by investigate the Mach cone to the theoretical and our simulating agent. So calculate it. Okay, let's took time. We use only 300 iteration. That's why it's so fast. Okay, our calculation is almost done here. So let's check the result. Okay, meshing graphics contour. Our contour is velocity contour and the magnitude is Mach number. So Mach number. Let's check the result. Save and display. Okay. You can see here that let's zoom it. That's the velocity contour. It's created a Mach cone here. That's the very similar to our theoretical. Let's goes into our theory. Okay, here is our theory. When the velocity Mach number is greater than 1, that means our jet is supersonic. The Mach cone is developed this type, a Mach cone that is almost 45-degree angle. So that is also called sonic boom here, and that sonic boom. So a sonic boom is produced by an aircraft moving at Mach number 2.92. So when the aircraft is moving this kind of Mach number, they are created a sonic boom, and the cone of angle is 20 degree. That is the reference line, and that is 20 degree. That is 20 degree. Almost 40 degree that Mach cone are developed. So you see our result that is almost similar that the theoretical result. so we can modify our result. So we use band, then color type, we change the color, we change the RGB color, red, green and blue, Mac format normal. Okay, then apply. Okay, it's look better now. Okay, yes. Okay, so our main target is to generate the Mach cone. So here you see the Mach cone for Mach number 0. Mach number 3 for a compressible fluid flow. Also we check the temperature variation. So let's go the result and see the temperature variation. Okay, Z axis. Let's took the contour. Okay, aircraft wind symmetry 1, then temperature. So okay, that is our temperature contour. And also okay, that is our temperature contour. So also check our pressure contour here. Okay, this is our pressure contour. So temperature and pressure are so much fluctuating here. You can see the density contour also. So density contour. So here is our density contour. So we see that the density is so much variant here due to the compressible flow, because we know that compressible flow density is so much fluctuating for the variation of temperature and pressure. So we see here. So simulation is too much important for the basic of our practical theoretical knowledge. We can justify our theoretical knowledge by simulating there. So you can save your result. So right click and zoom to feed view. Okay, then right click the picture, feed view, then okay, right click the picture, save your picture here. PNG format, use white background. So you can choose your file, my computer. So I save my geometry in CFD simulation. So aircraft wing simulation. Okay, let's save it. Okay, so let's check the value. So in aircraft simulation. So here is our main simulating result. You can see here. Okay. Okay. That's my video here. So thank you very much. Okay, close it.